This video will show you how to create a phase transition calculation using the property model calculator in the graphical mode of Thermo-Calc. In this example, we're interested in finding the phase transition temperature of sigma and how it changes with variations of material composition, as it is brittle and generally undesirable. The calculation is based on example number 10 of the examples listed on our website. To begin, open Thermo-Calc in the graphical mode and click on the property diagram template. We want to calculate a property diagram first so that we can get a good starting temperature for our property model calculator. We'll start by defining our system, so click on the System Definer. From the Database drop-down menu, select the FE Demo database, then select the elements iron, nickel, carbon, manganese, and chromium. Next, we'll set our composition. Iron is dependent, so we'll let that set automatically. Nickel is 1.4, carbon is 0.08, manganese is 1, and chromium is 17. This sets iron to 80.52. If you use the same materials repeatedly, you can save them to quickly load them in the future. To do this, name the material whatever you like. I'll call this one ferritic. Then click Save Material As. Decide where you want to save it and click Save. Now we'll start our calculation over so you can see how to load a saved material. Click New, then No, as we don't want to save our project. Now select Property Diagram again. From the Database drop-down menu, select the FE Demo database just as before, then click Load Material and select your material. Your elements and composition will automatically populate. Next, we need to configure our calculation, so select the Equilibrium calculator. Notice that the composition is filled in here as well. We'll use the default values for temperature, pressure, and system size, so make sure your values match mine. Also, be sure to use Celsius. We'll also accept the default variables for the axis definitions. Our calculation is now configured, so select Perform Tree at the bottom center of the program. Once the calculation is complete, a plot will appear in the results pane. We're interested in the sigma phase, which is represented here by the dark green line, so I'll maximize the screen over it so we can see it more clearly. When I hover my mouse where the sigma phase appears, we can see that the transition temperature is at about 596 degrees. So we'll round up to 600 degrees for the starting temperature. Remember that number because we'll use it in the property model calculator. We're now done with the property diagram. So right-click on the System Definer, hover over Create New Successor, and select Property Model Calculator. Notice that the composition we set in the System Definer auto-populates here as well. We're doing a phase transition, so click the Phase Transition model. A tab will appear where we can define our conditions. Because we're looking for the phase transformation for sigma, we want to calculate from any phase to sigma. We want to vary the temperature, and we want the search direction to be positive to negative, so leave those as they are. We just learned from the property diagram that sigma forms at about 600 degrees, so we'll set the upper temperature limit to 700 degrees and the lower temperature limit to 400 degrees to capture the range we want. The temperature, which is the starting value of the calculation, must be within this range, so we'll change it to 600 degrees Celsius. Remember, this is the temperature we got from the property diagram calculation. Next, we need to select our calculation type. We recommend that you always run a single calculation first to make sure the calculation is valid. So select Single, then select Perform. The calculation will run in the event log. When it is done, the last line of the event log will read, "The sub-process completed normally." If the calculation worked, you will see the temperature, and if it failed, it will say temperature NaN, which means not a number. If this happens, check your configurations. We got a temperature of approximately 596 degrees, which is the same temperature we saw in the property diagram and is the temperature around which our plots will be based. Because we got a number, we know that the calculation was successful and we can move on to a more complicated calculation. Select the uncertainty calculation type, which allows you to add variations to the configuration. We want variations in our composition, but not our temperature, so check the boxes next to each element. Starting from the top, enter 0.4 for nickel, 0.02 for carbon, 0.3 for manganese, and 2 for chromium. We will accept the default parameters of a standard deviation of 3 and a total number of samples of 200. To learn about the sampling parameters, visit the new Online Help feature by clicking Help, Online Help, then searching for Sampling Parameters, and selecting About the Uncertainty Calculations. Lastly, we need to add a plot renderer, so right-click Property Model Calculator, hover over Create New Successor, and select Plot Renderer. Now highlight the Property Model Calculator and click Perform Tree to run the calculation. We can see from the events log that the calculation is probably working because the temperatures shown there are all around 600 degrees. Once the calculation is complete, a histogram, also known as a frequency diagram, will appear in the results pane. The plot tells us how the transition temperature of sigma varies when we vary the composition. The plot will be slightly different each time you run the calculation because it is taking a random sampling from the composition range we set, so your plot may look slightly different from mine. Notice that the x-axis is labeled the relaxed condition. We can see which condition is represented there by looking at the condition to vary. In this case, it is temperature, so the x-axis shows us the temperature. The y-axis shows us the frequency, which is the number of samples out of 200 where the composition transitions at each temperature. We can see that transitions occur more frequently toward the center of the plot, near our 600-degree starting point, and less frequently at the edges. Again, the variations are based on the varying amounts of the elements that were sampled from Gauss distribution functions based on the deviations we set. For a detailed description of this, again, visit Online Help, search for sampling parameters, and select About the Uncertainty Calculations. You can see whether the plot follows the Gauss distribution by clicking on the Plot Renderer node and changing the y-axis to normal probability, then clicking Perform again. You can see that our data follow the Gauss distribution fairly closely in the middle, but less so at the ends, which is to be expected as there are fewer data points at the edges. To learn more about the Property Model Calculator, view the other examples videos we have available by clicking the links currently on the screen, or view our user guide, which explains how to set up calculations in all the models.